I can remember it like it was yesterday. I'm tearing open the gift on my birthday, and there is the original Nintendo Zelda 2, The Adventure of Link. I get the box open, and the cartridge itself is golden. Yeah, I said cartridge. That's how we rolled back then. Cartridge is golden, not like the gray, all the other gray cartridges that Nintendo has. And I slid it into the Nintendo, and I played that game for so many hours. I can still remember it. And essentially, you got your little character running, killing all the guys. You've got your stamina, right? Your life and your magic. And if this guy with the spear hits you, he goes, boom! Actually, that's almost the exact sound. This guy kind of flashes, little invisible, flips back, and then you go kill him, right? And you can only get hit so many times before your life is gone and you're doomed. Well, Cisco routers work almost the same. The little guys with spears are the tasks running on your router, and they're after your resources. And it's not like Windows machines where you can just kind of chuck stuff in a page file when your resources run out. On a Cisco device, if you run out of memory, you're done. You're dead. Your router reboots and starts all over again, and you have a major outage on the network on your hands. So this nugget is all about troubleshooting a router performance, really focusing in on CPU and memory utilization. Well, let's start off talking about CPU utilization. Cisco routers, unlike Cisco switches, do not typically have ASIC hardware available to them to do their routing. That's because they're so feature-rific. They've got all kinds of different capabilities that switches do not have. So essentially, your processor utilization will be directly equivalent to the traffic flow going through it. If you got a gigabit interface over here of 1,000 megs and 1,000 megs on the other side, and you are throttling that thing, you're going to see your CPU rise as it's processing more packets, right? Because the processor is having to look at the packet, look at the header, rewrite the data link information, check the routing table, all that kind of stuff is handled by the CPU. So before I even get to the content on the slide, know that your CPU will typically go up as you're utilizing your router. I decided to use one of my production devices to show this because obviously it's a little more exciting to see it on a router that's routing real traffic, right? So I'm on this router, which is actually a voice router at a data center. It's handling voice calls going through it. The command of choice all the time is show process CPU. And you will see when you do this, essentially the utilization over 5 seconds, 1 minute, and 5 minutes. That's a very valuable top line right there. And then it breaks it down to all the different tasks that are using that CPU utilization. First thing that I do is I always exclude 0.00% to get all of the idle tasks out of there, and my eyes are immediately drawn to the IP input because that's the one that is handling the traffic that's going through. Now this is a voice router, so the CPU utilization is not going to typically be related to the traffic because the traffic isn't actually that much. It's processing all kinds of voice calls that are going through it. I could do some show commands that show active calls that are happening right now, but it actually shows the phone number, and that may be an invasion of privacy on somebody's phone call that's going through this device. So one of the things that you want to look at is these 4 processes that you see in the background here. ARP input, net background, IP background, and TCP timer. These are the typical sources of extra high CPU utilization. And what I mean by that is something that you can troubleshoot. You can't really troubleshoot if you've got a gigabit router and you've got, a gigabit worth of traffic going through and your processor is pegged out because that's essentially what it's designed to do. You just kind of go, oh, well, I guess we need a bigger router. But if you're not seeing a ton of traffic, these are the typical culprits that can cause you to shoot up. The ARP input process is essentially the process on the router that is handling ARP packets, essentially sending out ARPs saying, hello, who is da 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 da, and then receiving the reply back. What can cause that thing to spike is a flurry of ARP packets coming from the router, and what can cause that, this is a typical culprit, is when you create a static route and you point it out in Ethernet interface. So I know some of you are like, what? Explain. So when you do a static route, let's just say you've got a router right here connected to a DSL modem or a cable modem, right? Because those essentially will give you an Ethernet interface into your device. Well, a lot of people will go in there and type in, I want to do an IP route, and they'll do like a default route, 0000000, and then they'll just, instead of saying 2, and then, you know, the public IP address will just say 174.1.1.1, maybe our carrier over there. Instead of typing in the IP address, they'll type in out ETH0 or fast Ethernet 0/0 or gigabit Ethernet 0/0, whatever kind of interface you have. They point the static route out the Ethernet interface. Now the router's smart. It knows, hey, that's a broadcast medium type. So what happens is anytime somebody out there sends a request, let's say you've got a server out here going to Google, you know, 8.8.8.8 to look up an IP address via DNS. Anytime it goes to that, it's going to hit the router, and the router will actually send an ARP message out for 8.8.8.8. What it's trying to rely on is something called proxy ARP, which is enabled on a lot of devices still to this day by default, to where some device out here, let's just say there's another router, will hear that ARP request for 8.8.8.8 and say, oh, well, that's me. Because it realizes, based on its routing table, that it is able to help you reach 8.8.8.8. So essentially, for every internet IP address, it's going to reply with itself as the MAC address. Now that's just one DNS request going to Google, right? But now imagine a production network where you've got 100, 150, 1,000 devices going to all kinds of different internet destinations. This thing's going berserk. It's like ARP, 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 you know, sending all these ARP messages out for them. Now the upstream router is happy to oblige and help you get there. That's the job of proxy ARP. But you're going to kill your router because its ARP input process is going to go crazy, right? So how do you see this? Now, what I usually will do is I'll use a little filter command. I'll say show process CPU, and I'll want to see this first line. So I'll say show me lines that begin with CPU, right? Which will be that first line gives me the key information. So I'm like, okay, that's good. Okay, show me, and I'll say I want this second line because that gives me all my headers. If I just look for the process, I'll see this information, but I don't have the headers. So I'll say show me something that has beginning with space PID, right? You have that space right there. You have to account for that. And then I'll do pipe, and I'll do ARP input. Now I know some of you are like, wow, that's a lot of work. Well, I'll usually do that in an alias command or something like that to check these processes out. And you can actually, you know, keep going with this list. You know, add in there net background, IP background into this same command and see them all at the same time. But you're able to see the process ID ARP input right there. That's the one I'm talking about. You can see the runtime, meaning essentially how much CPU cycles has this thing consumed. How many times has it been invoked, right? When the router needs to send an ARP, it's going to do this. And then you can see over the last 1 to 5 minutes, you know, very minimal. So I would say, okay, that one's not a culprit in this case. Next one, net background. Net background is the service that handles interface queues that are full. I'm like, it does what now? It handles when an interface is full. So essentially, as your traffic is going, let's just say that this is a T1 line on the right hand side. This over here is the gigabit Ethernet interface, right? You got a speed mismatch. This guy's sending in. This guy can't keep up on the T1 interface, so it starts queuing. Now the interface itself has its own little buffers. And by the way, that's same thing as Q. Q equals buffers. So it's going to hold those packets until it runs out. Now the router itself has some global queues that it's able to pull from to keep adding packets and not drop them. Now eventually the memory buffer is going to fill up and it'll start dropping packets if it keeps sending a whole bunch of data, but it tries to queue as much as it can. Well, the net background is the process of the router saying, hey, my interface buffers are full, can I have that global queue? And it's going to ping the CPU every single time it does that. So if you notice that this net background process is running a bunch, or it's eating up a bunch of CPU cycles, that typically means you've got a speed mismatch and you're sending way too much data for the kind of link that you have. So you can alleviate that by upgrading the link, if that's one of the possibilities that you can do. Or you can actually police the data on the inbound interface. So you can throttle it down to say, I want to cut it down to 1.5 megabits per second and match that T1 line. IP background process right below it handles the interface up-down states. So that's essentially when you have an interface that loses connectivity and comes back up, it's going to cause a little hit on your processor right there. I know some of you are thinking exactly what I am. This is invoked 21,000 times since this router's been running, which has been a little while. But essentially, this IP background process can go berserk when you have a flapping interface. One that's barely connected or losing connectivity quite a bit, and you'll see your processor peg when that happens. Last one is the TCP timer. TCP timer manages TCP sessions. So when I telnet to this device, or I SSH to this device, or any kind of TCP session coming in here is going to hit that TCP timer process. Now, what can happen is a denial of service attack starts really nailing this thing constantly because somebody's sending a whole bunch of half-open sessions, right? To where they say, the three-way handshake for TCP, right? They say hello, essentially SYN, SYN-ACK, ACK, exchange goes on. Well, a bunch of half-open sessions will cause this TCP timer process to eat up a whole bunch of cycles. It's a known denial of service attack, and that's why it's so important to protect your router by filtering TCP sessions to the router. I'm not talking through, I'm talking to the router by using an access list to prevent who can SSH or telnet into the device. Ooh, one more thing worth mentioning. If you haven't seen this before, this is like a poor man's SNMP monitoring utility. You can do a show process CPU history. And that will actually show you over the last, not too exciting year, but over the last amount of time, and you can actually see 60-minute averages, 60-second averages, what your CPU utilization is. So if you don't have a PRTG or SolarWinds-like system that can monitor this for you, this gives you a good feel for what this looks like over the last little bit of time. Okay, next piece is high memory utilization. This one is not as exciting as the CPU because Cisco equips their routers with enough memory to do what they're supposed to do. So I guess in that sense, it is exciting that you don't usually have to worry about it. So why are we talking about it then? Well, 4 reasons. Number 1, cause of memory shortage, and this is in the TAC case library, is not meeting the minimum requirement for the iOS version that you're running. Essentially, people get a Cisco device, they buy a software upgrade, but don't realize that all the different iOS versions and their feature packs that come with them essentially require different memory amounts. If you have an IP-based feature set, it's going to require a different amount of memory than an advanced enterprise feature set. So you'll get the iOS and then put it on there, and it seems to run fine for a while. So either you purposely and like, hey, seems to work, or you negligently negligently put that iOS on there, and the router ends up crashing every 5 days or something like that because it just runs out of memory. Or when the tide is high, essentially there's a lot of stuff happening on your router, that's when it bites the dust. So documented TAC cases, that is the number one cause of memory shortages. Number two cause is a memory leak. Believe it or not, there is iOS bugs out there. So you'll know memory leaks are happening by monitoring. That's one of the key things. I'm going to show you a command. Let me show it to you right now. You can do a show processes memory, right? And you see it's just like show process CPU. You can see here's the total memory, here's what's free, and you can scroll down and see what's using what. But unlike the CPU, it's not like it's like, oh, there's my smoking gun right there. That must be, you're like, okay, well, it seems like that's using a license auto. That doesn't seem. So the only way, right, that you're really going to get any accurate gauge of this is by using something like this. Got to bring it on over. This is PRTG for this device, where I can actually see the memory utilization. You can see it over time, go through the history, and say, okay, well, there's been 79% free, and there's, for a long time, I can go back and back and back and back. This is obviously right now, but you can go way historic on this thing, and see the memory utilization to see if it's slowly ticking down. That's how you know what's up. Is a memory link will slowly nudge down on that graph depending on the severity of the memory leak. So most of the time you just gotta upgrade the iOS. If you're looking at syslog messages, you will see something that says mallocate_fail. Or something around that verbiage when something's really about to go wrong. So essentially, when you see these syslog messages, the router is trying to allocate memory to some process, and it's like, I can't because I don't have any memory. So if these start showing up, it's only a matter of time before that router goes and ends up rebooting because it ran out of memory. Same thing here. You'll see buffer leaks. If you do a show interface command, matter of fact, let me bring it up right here. No, I can't use that production router. Essentially, if you do show interface command and you see, where I'm talking about when you're going down there, you've got the input and output queue where it shows 0/0 or whatever case, however many packets it's waiting in queue, and it's got something like that, right? Well, if you ever see these things exceed, like you've got a queue of 75 packets that it can hold on in the interface, and it says something like 76 or 90 or some bigger number right here, you've got a buffer leak, which means there's a memory error allocating memory for the interface as it's running out of queue space. It obviously happens a lot because that is the number 3 TAC case for running out of memory shortage. Again, the solution to both of these is to upgrade your iOS to a patched version. Last, and I know I feel like I'm talking a lot on this, but let me just mention this one thing. It pays to use an iOS that is golden, meaning you will see iOS versions coming out daily, it seems like, with T version 92 or whatever the case is, and while that may have some cool features in it, I used to be like one of those upgrade people. Like anytime there's an upgrade, I'm like, ooh, I want that because the newer version is always better. That's not the case. Cisco has a golden version. You got to stick with the master, essentially the one that is tried and tested. They always, when you go to their website, will say, we recommend this, but there's these newer ones available. Don't do it. Just stick with the tried, tested, and true one unless you have a very specific reason for going newer. Last one you can see is BGP. BGP has a massive routing table. If you've got a router that not only can run BGP, but doesn't meet how much memory you have, you're gonna max that thing out because it stores the routing table, not just the BGP routing table after the fact. It actually stores the BGP table, which is the full table from multiple ISPs. You watch your memory drop like a rock when you run full BGP on a device. Last piece of advice I have is don't resurrect the past. Just looking at that picture, the thought flashed through my mind. I go, I should go on eBay and go get a Nintendo with Zelda 2 and just play it again just for old time's sake. I've done that before with Mike Tyson's Punch-Out, and it totally ruined the game. I'm like, this is so lame. How did I think this was cool? It like defiles the memory. So don't do it. Leave the past in the past. Anyhow, I hope this has been informative for you, and I'd like to thank you for viewing.